Hey guys, we're going to be taking notes for our very last topic from, instead of me writing them down today, from me recording my computer screen because we're going to be using Desmos a lot and we're going to just need the computer more than actually handwritten notes. So this may feel much more like normal class. Whatever page you're on, who knows that we would be writing this in, but this is our very last page of notes for algebra. And if we were in class, we'd probably be crying as it is, or I would be crying at least. As it is, I cannot see your faces, but as you are writing down the title Curve of Best Fit, or otherwise known as Quadratic Regression, I just want to take a second to say that I have really enjoyed having you all in class, some of you for 2 years, some of you for less than that, but it is kind of the end of an era because even if you've only had me for 1 year, we have taken a lot of notes together, and so this is the last one, last page, Curve of Best Fit, Quadratic Regression. So take your time, just appreciate, take your time filling that in, y'all. It's probably a good thing I can't see your faces, or like I said, I'd be crying. So let's get through this last topic, and we will finish this course out. So, curve of best fit and quadratic regression. If you think back, probably even before Christmas, instead of talking about a curve of best fit, we have already learned line of best fit, right? And so if you will remember just really quickly what a line or linear regression looks like, we typed in some data points and we would find a line that best fit the data, meaning that a line would either go sort of like this, kind of through the data. The data wasn't always on a straight line, but it formed in general a line, and we called that positive correlation or direct variation. And then sometimes we'd have data that went down, and so we would create this line of best fit that went through the middle. And if you will remember typing this into Desmos, first you had to type in some data from a chart. So you would have been given some data, and it would have been X's and Y's, and you would have typed all that in, right, here and here and here and here. And then you would type in this formula, and it was Y1, and then that little squiggle, that tilde, or the approximation sign, M, and then X1 plus B. And so remember, your Y1 and your X1 corresponded with what was in your chart over here, because these actually had ones next to them, and we had to make sure that this was always a 1 and this was always a 1. And in general, the formula for a line, or the form of the equation that it takes, is always y is equal to mx plus b. So because this is our linear equation, this is how we were able to find what was called a line of best fit, or what we called linear regression. And so today we're going to be talking about quadratic regression. And for a quadratic graph, we're going to have data that kind of fits a curve. So we've been talking about quadratics or parabolas over the last couple weeks. So we're going to actually find a curve of best fit, because a line would not model this very well, but a U shape does. And so we can either have, again, what we learned last week was called concave down, which means that it's an upside down U. Or we can have a model that is going to, in general, again, the line's going to go through mostly through the middle of all this data, that is going to be pointed up. So concave up. And so we're going to have some data that fits this. Now, you might be asking yourself, well, why would I need to ever see data that looks like this? Well, I'm going to show you, using Desmos, how we can create the scatter plot of data and generate a curve of best fit. But first we need some data. Flip over here to this activity. Now, this is an activity we would have done in class, but I just want to show it to you so you can watch what would have happened. So it says create a line of best fit, drag the line so that it fits these points. Now, if you notice, I cannot get a straight line to fit very well through these points because they are sort of curved, right? They do have this little bit of curve. It almost looks like, if you can imagine this as being a ball flying through the air, it's like the ball's going up, but eventually the ball's going to fall, right? And so this is just to illustrate that lines aren't always the best way of modeling something. And so you can see this picture being overlaid on top of the graph. Actually, it's a model of a basketball flying through the air. So if you think about just shooting a basketball in general, because of gravity, when you throw a ball up in the air, eventually it hits this peak and then it falls back downwards. Well, that's good because we want it to go through the hoop in the first place, right? And so we would, think about the vocabulary we learned last week. There is a y-intercept right here where the basketball is beginning to be shot. There's going to be a vertex, and then there is going to be a place at which the basketball actually flies through the hoop. And a line does not model that well, right? The linear regression that we learned before Christmas is not going to do very well here, because if this were a line, the basketball would be shot and then would just continue flying off into space. But we know that that's not what a ball does here on Earth, right? Again, because of gravity. So we're going to look at what again, quadratic regression would look like. A curve of best fit, if you will, instead of a line of best fit. And so we're going to make some predictions about this basketball. All right, so here is a video of a guy shooting a basketball. We're going to watch it. So the question is, what's your best guess? Is this ball going to go in the hoop, or is it not going to go through the hoop? If we were in class, I would have you all click in and out. You can say your guess out loud. I think, though, it kind of looks like it's going to go in. So I'm going to submit that answer. And we're going to do a second example as well. So watch this video. Is this ball going to go in or out? And so it looks like the vertex is a little bit higher than maybe the last one. And if you were to predict kind of what was going to happen out here with the rest of the data points, I think it looks like this basketball is going to bounce right off the back of the backboard. Now, might bounce back in. I'm going to say this one's going to go out. So now we're going to analyze these shots. So this is shot number one, if you think back to the first one. And if you can see, we're going to make a curve that is going to best fit the data points that we have for our basketball here. And now, if you see this line, what does it look like is going to happen to the basketball? Looks like it's going to go right through the hoop. And so if you can see, the curve of best fit helps us better to see what's going to happen in the future. So I'm definitely going to stick with my guess about shot number one, that it's going in. All right, shot number two. Now, if you remember, I guessed that this one was going to go out. So I'm going to use my curve of best fit. I'm going to, again, sort of predict what it's going to look like. Now, again, if you can see, this line now lets me know that, yeah, this is definitely it's definitely going to hit the backboard, but it may bounce back in. So originally I said out. I'm still going to guess out just to stay consistent. All right, so now we're going to see the actual answer. So here's shot number one. We predicted it was going to go in. It went in. And you can see the data points here of the basketball sort of flying through the air. They've sort of screenshotted what those data points would have looked like. And this basketball does indeed go through the hoop. And our line helped us see that a little more clearly. Here is shot number two. Now, I said that one was going to go out. And again, our line pretty much confirmed that it was going to hit a little too far back and that it doesn't actually go in. So I predicted that the ball goes out. My parabola with the curve of best fit said it was going to go out. So we did pretty good on that one. So now that we know where the data comes from, we're going to look at a couple of examples. So let's start with basketball. If we were in class, I would be giving you this data and you would be typing into Desmos. You might want to split your screen between this video and maybe having Desmos open so you can do this example with me. So it says the time a basketball is in the air versus its height as it travels. And so we're pretending we're shooting a basketball in the air, and at zero, at the beginning of the time, it's at a height of 5.5 feet. That's basically where I would start to maybe shoot a basketball. And then after half a second, it's 6.1 feet in the air. And then after 1 second, it's 6.6. So notice it's going up as time goes on. It sort of reaches its peak right here at a height of 7 feet and 8/100ths of another foot. And then notice as time goes on, it starts to come back down, right? 7 feet, 6.6, 6.1, 5.5, and we're assuming that that would be sort of somewhere where it's actually going through the hoop. And so we're going to type this data into Desmos. So I'm going to bring up my Desmos screen. I'm going to split my screen so that I can see my data. And so I'm going to insert a new table. Remember, that's the plus sign, and insert a table. You want to ensure that your titles in your columns here is the X1 data and the Y1 data. And then we're just going to type in the data that we're given. And so at 0.0, you could really just put 0, but I'm going to type it in exactly as I see it. The height was 5.5. And at 0.5, the height is 6.1. And at 1, or 1.0 feet, the height is, or at 1 second, excuse me, the height was 6.6. And 1.5 seconds, the height was 7. 2.0, the height was 7.08. 2.5 seconds, the height was back down to 7. After 3 seconds in the air, the height is 6.6. After 3.5 seconds in the air, the height was 6.1. And after 4 seconds in the air, the height of the basketball was back down to 5.5. Now, I'm going to click my home button because my zooming ability here was a little bit off, but if you zoom in, you go back home, you can tell that this data forms a nice parabola, right? It goes up, it goes back down, it's concave down, which means it's pointing down, but it follows the pattern of what a basketball would look like flying through the air. So now, linear regression would have had us type in y1 and then the tilde and then mx1 plus b. This is what we would have done. But notice, a line is definitely not going to model this well at all. Actually, the line looks like this basketball should be shooting straight out. And so we know that that's not good. Now, if you will think back to what a quadratic or a parabola looks like, in general, our form is y is equal to ax squared plus bx plus c, right? That is in general the form of a parabola. We've got an x squared term with an a out in front of it plus a b plus a c. And that's our general form of what a parabola or a quadratic function looks like. Now, of course, we're going to have to make some modifications to this to make it give us our curve of best fit. So first thing we're going to do is anywhere I see a y, I'm going to put a 1 next to it. And that refers back to the y1 here. All right, now it went away, but that's because we've still got some errors down here. We're going to change the equal sign to the tilde, of course, to make an approximation line. A is going to stay the same. That's our coefficient in front of our x squared. However, for this x squared, I'm going to have to put a 1 next to my x in order to make it recall up here that we're dealing with x1 data. Now, your 1 is going to go right below your square, and that's going to look a little funny, but that's okay. And then the last thing we need to do is go over here. The plus b is fine. B is the coefficient. But because we've got another x here, we're going to put another 1 because we want to make sure that it's looking back up here at the chart. The function is and saying, okay, I'm dealing with this data. And if you notice when you do that, when you type in y1 tilde ax1 squared plus bx1 plus c, the general parabola formula, you are going to get this nice curve of best fit. And we've got some numbers down here below. Now remember, their linear regression used to give us an m value and a b value. In this case, we're going to get an a, b, and a c value. And so here's how we're going to write our final answer. So we are finding this curve of best fit that will model our data. It looks really nice. And so our final answer is going to be y is equal to, so we're just going to copy down what we see here. Y is equal to in this case, right, because we have, we've now used our data, so we can put an equal to. The a value is going to be this right here. So where we see an a, we're going to plug in negative 0.39, and I'm going to round it off to 3 decimal places. I'm just going to say 0.397. X squared, that's the a value is the coefficient in front of the x squared, and then we're going to put plus, and we're going to write our b value that it gives us, so 1.5, and again I'm going to round it off to 3 decimal places, and so that would be 5, 8, 9, that 6 is going to round that up to a 10, but that makes that a 90, so I'm just going to put 1.590x, and then our c value, which we're just going to plug in here, plus c, which is 5.459 if we round it off to 3 decimal places. And so that is going to be our final answer. That is the equation of the curve of best fit that best models our data and predicts what is the data going to do as this basketball continues to fall. Because notice we didn't have any data down through here. Instead of, sometimes when you're writing or typing your final answer, when you're going to see it on quizzes, instead of seeing a y, sometimes you might see f of x. Remember, that's just function notation. So if you come across that, that's fine. It's this piece right here, though, that's not going to change. This a, b, and c value comes from your quadratic regression line, and you're just going to pick out the a, b, and c. And if you'll remember, something I skipped over here is the r squared value. Remember, that tells you what percentage this line is accurate. And so this r squared value actually tells us that, hey, yeah, the curve that you generated here is 99% accurate, 99.32% accurate as a percentage. And so maybe take a second if you're taking down notes, take a second to write this down. The thing that you are going to have to remember when working through these problems on quizzes and your quiz this week is this regression formula. So y1 squiggle or tilde ax1 squared plus bx1 plus c. This is your quadratic regression formula. And x's and y's have to have those sub 1s next to them. And this one's going to look like a parabola, ax squared plus bx plus c. All right, let's do another example. So I'm going to close this out, get rid of my data, and let's find another example. All right, so let's look at one more set of data. And so we're going to be given some data over here about the year versus the number of flu cases that were positive that year. And so I'm going to type in my data over here. Again, table assure that this says x1, y1. I'm going to type in 1999. All right, so my data is in, and again, notice my y-axis is only going up to 15 right now, and my y values are 400. So I'm going to have to do a little bit of zooming out. Let me make Desmos a little bit larger here so we can see it. I'm going to zoom out. Aha, and over here next to the year 2000, of course, my data is here. Now, it is a little hard to tell right now just because the years are so close together and the data is so close together, it's a little hard to tell exactly what's happening. But because we're talking about quadratic regression, you may be able to tell that as time goes on, as the years pass, here was the first year, and that was in 1999, and then in 2000 the number of cases went way down, and then in 2001 the number of cases went down, but in 2002, which is this dot right here, they started to go back up again. And so we can tell by the years passing that we almost have a U shape here. So we're going to do a curve of best fit, or a quadratic regression line, in order to show us what our model should look like here. So we're going to type it in. y1, remember this is the formula that you need to keep in mind in all of these problems that you're doing this week. So y1 squiggle, and instead of m, we're going to type a x sub 1. Make sure every time you have an x or a y that you put that 1 there. In order to get the squared, you're going to have to go down here to your keypad and actually hit the square button in order to make it go up in the air. And then plus bx, again you've got an x, make sure it says a 1. If you're getting this error message, it's even if you hover over it, it's telling you x may not be used as a regression parameter. We want it to be a regression parameter. We want it to have a 1 next to it so it knows we're talking about this data up here. So put the 1 next to it plus c. And so as long as you have that typed in below your data, then you are getting, notice you're getting a, B, and a C value. Now, our C value here is really large, and you're not going to get any that large when you're doing your quizzes, but just remember that 10 to the 7th power means that we're going to have to move the decimal over 7 places, so this is going to be a really large number. C value here actually comes out to be 38334, and then we would have to have 3 more zeros in order to move that decimal over there. 1, 2, 3, 4, 5, 6, 7. Now, you will not have to do that in your quizzes, but that's what that means if it comes up. All right, and so our final answer, or the answer that you would click in your quizzes, would be, for this problem, you would put y is equal to, A is 9.5 7, 1. Again, I'm going to round it off to 3 decimal places. And that's going to be x squared plus our b value is a negative. Now, you can either put plus negative that value, or it may just be a minus sign, right? Oops. And so I'm just going to change this instead of a plus sign because it's a negative value. I'm going to make this minus 3 point, oh, excuse me, not 3 point, 38309.9, and that's going to have an x next to it because that's our b value, and then it's going to be plus this c value, which we've already said is something as large as 383340000. And that is how you find quadratic regression equations.